I'm going to leave that there and let you guys write down some of that. And this will be a good guide to use throughout today. We're going to be using these things. One second. I'm starting to forget what I'm saying now, so I gotta actually write this down. You know, there's like waitresses that take your order and I'm gonna write anything down. And you always think people forget. Alright, I'm going to scroll down just a little bit more so you guys can see the very bottom if you can't quite. Give me a thumbs up if you're done with this. Okay, I got a couple more rules here. right, I'm going to scroll back up just for a moment to talk through some of this, and I'm going to walk us through an example as we go. So yesterday, I thought we would actually go through a bit more examples, and so I wanted you to have a chance to at least try them on your own first. Some of you guys did a really great job of actually going through the process of counting your valence electrons, giving me a skeleton that made sense in terms of the symmetry of a molecule. And I saw a couple that you guys went all the way through, and you're like, okay, I think I got this. So you're going to have a really, really good start on this. But the structures that you've drawn, we're going to be building in a lab. We'll see if we get to building some today. But we also have to talk a little bit more about the molecule as a whole, the shape it takes on, and how does it impact like all of its properties. So we're really like zoning in on a molecule, right? So we're talking about something that's itty bitty. And we have to continue to create models that look like the molecules so we can understand why the molecules matter. And so, big idea, like the Nobel Prize winners yesterday were about molecular machines. So if we can like manipulate how a molecule looks or the way it acts, then we can do everything with it. So we can deliver medicine to specific cells. The one molecule yesterday, molecular machine, was something they're going to be putting in cell phones to cause it to do something different. I have to like actually look into the literature on that one. So I'll pull up the Nobel Prize winners. But there's like a really cool amount of research going on about molecules, and we're just like barely touching the topic, but it does matter like in the big picture, the big world, not our world. Okay. So this right here basically is exactly what we were doing yesterday. It's just got a bit more detail for you. So whenever you guys were drawing your molecules, the very first thing you did always count your valence electrons, yes? And then you had to make a skeleton with a central atom. Generally, carbon is going to be our central atom because it loves to bond, specifically 4 times. Why would carbon want to bond 4 times? Look at its valence number. Emily? Well, it has 4 valence electrons, so it has room for 4 more. So that's why it wants to bond 4 times. So it loves to be in the middle. If you don't have carbon, then choose the singleton, or the one you have a single atom of. And if you don't have a single one, or sorry, if you have 2 single ones, like there was one on your homework that was XeOF4, I think it was F4. It was on the right-hand side. Yeah. So you've got 2 single ones. You got xenon and oxygen. You're like, well, which one's going to go in the middle? Go with the largest ones. Who's largest, xenon or oxygen? How do you know? Because, no, we're talking about largest atom. I don't see anybody doing this. Thank you. Atomic radius. Xenon will be the biggest. Oxygen's like way up here. Xenon's way down here. So it actually is the biggest. Okay, so once you've added, kind of created your central atom layout with your atoms around it, when we bond all the atoms to it, I kept calling them legs, like, you know, add a leg here, here, and here. The term truly is ligand. Let's just think of it as an attachment. And as you're going, you're then going to make sure everybody has octet. However, the octet rule is like only 50% of the time followed. It's really a guideline. You're going to have some things that have less than octet and some that can expand octet. And the rule of thumb is less than octet are things that are smaller than, look on the periodic table for me. Yesterday we talked about hydrogen being so small and helium being so small. What was their rule of thumb? What was the number of electrons they could accommodate? 2. So the duet, right? Well, things that are approximately the same size as our same number of electrons as them. So hydrogen, helium, lithium would never form a covalent bond, nor would beryllium because they're metals. But like boron really, I was gonna say carbon, but really it's boron. So hydrogen, helium, and boron are okay to have less than octet. Helium generally will not bond either because it's so teeny tiny. Yeah.
How would it lanthanide actinide become an ion?
That's going to be another story. Can I talk about that one a little bit? Okay. So expanded octet would be things that have access to D block orbitals. So here's the story. We know that this. Look on the periodic table again here for me. So we have like sodium, magnesium. That's like 3s2, correct? Yeah. Mm-hmm. And then we have 3p6, right? Where's the next 3 one come in? 3D, right? So if you're in the 3rd energy level, like phosphorus, sulfur, chlorine, argon, you're in the 3rd energy level. You're in the 3p. You still have access to the 3rd energy level in terms of the d orbitals as well. So if you somehow attain more than 8 electrons, you can just throw them into the d orbital because the 3rd energy level is where the d orbitals start to build. So that's something called expanded octet. We're going to do a couple examples with that today. But regardless, we still have to try to meet octet. Maybe it's more, maybe. And if we have to rearrange electrons, we will. And that's where we're going to start about double bonds and triple bonds today as well. Okay, so as I draw, you're drawing, and then we're going to try to build some. There are molecular modeling kits at your desk. I'm just going to go through a couple models with you, and then you guys are going to do the rest. Okay, can I go from here? Yeah.
Are we going to go over the sheet?
I'm going to go over examples to help you with the sheet. Okay, because your sheet is your lab, and I'm not going to go through and draw all the ones in your lab. Okay, so we did ammonia yesterday, yeah? We did this one as well?
Yes.
We did both of these. Okay, I'm going to go through and go through the next couple of examples. So, I want you guys to start off with this one for me. SO2, and I want different groups to tell me where our steps are in accordance with the rules of thumb here. So, Miles group, you guys tell me, how do I start? Okay, so sulfur, I'm starting with this one, okay? Sulfur, look at, everybody have your table out? Okay, how many electrons, valence electrons group does sulfur have?
6.
Okay, so we have 6 from sulfur, plus 2 oxygens, which each have 6 as well. Okay, so 12, 16 is what? 18 valence electrons. Okay, so we've got 18 valence electrons to work with. Lindsay's group, Lindsay's group. Go ahead and tell me the next step. Okay, so who's the center? Sulfur. It's the singleton, right? So it's the one in the center. And I'm going to go ahead and put the ligands or the atoms attached to the central atom. Okay, and there's only 2 other ones, so the 2 oxygens are going to be attached. And we try to make it symmetrical, so left and right, or up and down, however you want to do it. Okay, so far so good. This group over here, what's next? What's my next step?
You want to add the extra electrons?
To what?
Oxygen.
Yes. Let me finish drawing the structure real fast, stretching. All right, so I need to give can you tell me specific numbers? So like how many more does this oxygen need?
2.
Hold on. So this specific oxygen only has 2 electrons that it's surrounded by, right? It needs 6 more because it needs octets. So I'm going to put these as lone pairs. And yesterday I was saying lone pair, but I want you to know that I'm saying this. Lone pairs of electrons. Because they're all lone, right? They're just a pair of electrons out on the outside. But these in the middle, these are called bonded pairs because they're bound, right? They're holding the atoms together. All right, so everything still needs octet, right? So this oxygen over here also needs 2, 4, 6 more. And wait a second, this one in the middle has what right now? 4, so what does it need? 2 more lone pairs, right? So 1, 2, 3, 4. Okay, so at this point, I have achieved octet for everybody. Cool? Now we need to kind of go back and see how many electrons do we have? Do we need to add pairs? Do we need to take away pairs? Do we need to make them share? So this is where the rearrangements come in. So count with me. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. I have a problem, right? How many should I have? 18. So we went ahead and gave everybody their own electrons. But this is a covalent molecule, right? They can totally share. They're sharing 2. Why not share more? So here's what we have to do. All we have to do is take away 2 electrons from 2 atoms and then put them as a bonded pair in between. So I'm going to take away the sulfurs and 1 pair from the oxygen and go, look guys, you can't have 2 by yourself. You're just going to have to share. I've made a double bond now, right? I'll take questions in a second. I'm not quite done yet. So after I've made this bonded pair, this double bond, I now have actually 18 in my structure because I took away 4, which brought me from 20 to 16, right? And I added 2 back, so I'm back up to 18. So if you double check everybody's counts, you should still see this oxygen here, and you don't have to circle yours, I'm just showing you here, 2, 4, 6, 8. Yeah, there's 8 there. This oxygen over here, 2, 4, 6, 8, we're good. And then the sulfur is surrounded by 2, 4, 6, 8 as well. Everybody has octet. Yes?
I'm very confused as to how to do that.
Okay, I'm going to do some more examples. So I'm going to hold off for more questions at this point in time. Okay, so all we did was we counted up 18. We saw we had 20. We dropped off and said we can't have this many. We eliminated some and added them as a double bond instead. That right here is going to give us a specific structure. I'm going to show you guys how to look at structures now. On your sheet in front of you, you have a little chart that says VSEPR theory. and it has different shapes, and it has different lone pairs and ligands. I want you guys to look at this for me right now, and let's go ahead and determine, from sulfur's perspective, its shape. So the way you do this is you have to consider the central molecule. So the central is the one you look at, is key, okay? So according to the central molecule, sulfur, how many lone pairs does it have? How many lone pairs does sulfur have? Look on the board, or look at your structure. One pair, right? So it's 2 electrons, you're right, but it's 1 pair, so it has 1 lone pair. Okay? According to sulfur, how many ligands does it have, meaning atoms attached to it? 2. One is over here, it's attached with a single bond. One is over here, it's attached with a double bond. It doesn't matter how it's attached, it just has 1 leg and 1 leg. So it has 2 ligands, right? Correct? All right, so if you look on your chart, you should be looking for 1 lone pair, 1 ligand, and what is that molecular shape? I mean, sorry, one lone pair and 2 ligands. So you see 2 ligands, 1 lone pair is bent, correct? So let's just stick with the molecular shape for now. We'll talk about the electron group geometry later. So, does this look bent to you? Does it look bent? No, it looks like a line, right? I can draw it looking like a dinosaur, people. It's not a dinosaur. Whatever you draw may or may not look like it truly should look. Pull out your molecule kits. Let's go ahead and try to build this one. And I'm going to prove to you that it's bent. So, one person is your group, you built your group. I want you to find an atom that has, I can build some mine on. Fine. Go ahead and take the yellow colored one, and let's call this one sulfur. The oxygens are red, so oxygens will be red. And we need to go ahead and attach this with the number of bonds it needs. So I'm going to go ahead and model this for you. You have little single, tiny, straight gray bonds. You're going to make 1 bond on one side. So I'm doing the right-hand side on the board right now. So I'm doing an oxygen attached. So I'll take one of the red ones, and I'm going to attach it. Done, right? So there's sulfur and there's oxygen. Now on the left-hand side of this molecule, my left, sorry, now you see a double bond. You're going to notice that these little tiny, straight, stiff ones, they don't bend at all. You can't really make a double bond on the side because you can't put 2 on there in the right direction. So that's where you take the flexible, the really flexible bonds, from the ones that are long and skinny, and we're going to attach it to sulfur. But we have 2 little flexible ones, so we're going to put one on sulfur, the other one on sulfur. Okay, looks like it's going to have 3 legs, right? But wait. Now we're going to take our another oxygen, and we're going to bend them so they fit on sulfur like that. So you have like a double bond like this. They have like a little curve to them. And you hold up your shape and tell me what shape that is. What does it look like? Does it look linear? Does it look bent? Yes. Though I have drawn it linear, you will see yourself drawing it just like however it comes to mind. It does not mean that is the shape. You have to think visually how it would look in 3D space in terms of the molecular geometry. So what's this hole on top? Show me your sulfur. You have a hole on top, right? What is that? Say again? The lone pair. Okay, so it is the lone pair. So let's pretend, put your arms out. Your hands are oxygens, okay? Let's call your head sulfur. Okay, your head is sulfur. Now, I've got my arms out straight, right? What are these bonds made of? What's in the bonds? Electrons, right? Electrons are negative, right? Lone pair. What's in the lone pair? Electrons. What do electrons and electrons do to each other? They repel. So these electrons that are up here in your head, they're repelling these on both sides, which is why that bent structure occurs. Because this lone pair up here and this lone pair, they don't really want to be near each other. They're both negative. So that's why they can't stay like this, because they're just too close to each other. So they have to bend down like this. So that's called the VSEPR theory, valence shell electron pair repulsion theory. Repulsion. Okay, so let's do another one. I'm going to do phosphorus pentachloride. Now, this is one where we're going to talk through expanded octet as well. Yeah, you can deassemble that one. And then we're going to build this one as well. Okay, work with me. I'm going to try to do 1 or 2 more. Mixed group. Tell me the first step. Okay, so you guys are sure how many phosphorus? Look at the group number that phosphorus exists in. 5. Okay, so phosphorus has 5 valence electrons plus 5 chlorines, which each carry somebody else in your group. Chlorine has how many? 7. So you guys are writing down this example with me as well. So we have phosphorus with 5 electrons. We have each of the chlorines with 7 valence electrons. So that's a total of what? 40 valence electrons. Okay, so that's what our goal is in the end. This group up here. Somebody tell me what our next step is. Why phosphorus? Singleton. We put the singleton in the middle, so phosphorus goes in the middle. And then what else next to the same group? 5 ligands. And I'm just going to kind of make like a star shape, kind of as equally as I can. And it doesn't matter as long as they're kind of symmetrical. And we're going to put 5 ligands or 5 chlorines on there. Okay, this group over here, Kyle's group. What's next?
You're gonna add up all the electrons. Or
Not quite yet.
one was like
Distribute electrons until when?
octet.
Until octet. So let's go ahead and do that to chlorines. Let's go ahead and add 2, 4, 6. Okay, 8. That's good. 2, 4, 6, 8. That's good. 2, 4, 6, 8. That's good. 2, 4, 6, 8. That one's good. 2, 4, 6, 8. That one's good, right? Okay, what about phosphorus? How many does it have? 10. Is that okay for phosphorus? One would say no because we think octet rule, we don't break the law, right? But what did I tell you about group 3? It has access to D block. So what you'll see is phosphorus, sulfur, chlorine, and argon, those 4 right there. I know they're in 3 key, but that means they have access to 3D because they're in the same energy level. So phosphorus, and I'll write that note right here, can expand octet. And I'm just going to put 3P to 3D like that, and I hope that you can abbreviate that for yourself. Yeah.
Can you do that with the other levels, the other things? Like
Yes. Anything past, because 3 is where the energy levels start, right? So anything past 3 you can also do it with, yes.
could you use the lanthanide and that?
Generally we will not be going that far because there's already 10 electrons more in the D block. There's no way in Hades we're going to get down to like 20, 24 extra ones. Just maximum, it's usually just a couple. Like generally I think it goes 8, 10, 12, not really past that. Yeah. Let's see here. 7 would be xenon. No, I'm sorry, I can't read. 1, 2, 3, 4, 5, 6, 7. Yeah, and trust me, we'll never do one that big ever. Okay. All right, let's go and finish this one. I'm not quite done with this question. 1 second. So we now have it distributed to octet. We've considered phosphorus as an outlier. We have it having 10. That's totally fine. Next step is to now to count them up and make sure we've met 40, right? I'm counting by 8s here. 8. Go ahead. 16, 24, 32, 40. Yes, we have it, right? Okay, now let's go do our geometry. Geometry means, look at the who. Who do we always consider? We are looking at the Vesper theory, but we're looking at the central atom, right? So phosphorus is what we're looking at. How many ligands does phosphorus have? 5 ligands. How many lone pairs does phosphorus have? None. 0 lone pairs. 0 lone pairs. Look on your sheet. Tell me what that shape is. Huh? I don't have it on your sheet. Okay, I want you to build it. Build it. Find one with 5 holes. So you could probably have 2 buildings if you want, but that's easy enough for that structure. All right, hold it up when you have it built. I want your team to come up with a shape that would describe that. Think geometry, think prisms, think that's what Matt Warren has. Emily, all right, raise your hand if you have this. Okay, we're holding it in this orientation. I want you to think about what you could call that shape. I'll draw it on the board as well. I'm trying to draw 3D. Don't laugh. It's going to be bad. Okay, it looks just like a bunch of lines, but here we go. Bunch of lines. This is kind of what it looks like, right? Okay, if I were to assign this, what would you assign? So the thing in the middle, what shape is that? A triangle. And if you look at the top, doesn't it kind of look like a pyramid? Okay, but how many pyramids do we have? 2. So here we go. Trigonal, write this down. Trigonal. And how many pyramids did you say?
2.
So what's a good prefix for 2? Bi. Okay. Bipyramidal. Trigonal bipyramidal. Can you see it now? Can you see that structure and it looks trigonal bipyramidal? You're supposed to say yes. The answer is only yes. So look, if you hold it with the 2 guys pointing up and down, the one in the middle part is a triangle, and there's a pyramid on top, and there's a pyramid on bottom. Okay? I'm going to do one more, and then we are going to do a couple more modelings by ourselves. All right, we're going to, hear the beads hitting the floor. I want you guys to all start nitrogen, diatomic nitrogen. Yeah, some of these made a point. These are on the 3 of those so far are on your sheet. The 2 of them are on your sheet. I'm doing that with purpose. So you can check yourself as you go. So Carson, you're up, man. Tell me what I'm starting.
You put the, like, connect.
Whoa, man. Whoa. Step 1.
You have to count.
Yeah. So I'm just trying to save you from yourselves because all of you were like, I can draw this. I'm a beast at this now. No. You still got to count your electrons because then at the end you will have some fact check on, right? So 5 valence electrons for nitrogen times 2, right? So we got 10 valence electrons we're working with. Now, go ahead, Carson.
Then you draw
The nitrogen's attached to the nitrogen. Do we have a central atom here? No. They're both just like, hey, we have to attach. We have to hold hands here, okay? So as we're holding hands, what do I now need to do? Let's go through EJ's group. Octet. Okay, ready? What do I do? Add pairs. 1, 2 pair, 3 pair. So that nitrogen here is 8, correct? And then over here, 2, 4, 6, 8. Okay, done. How does that look to you guys? Too many, right? So this is your thought process. You're like, I have to give everybody octet. So you do. 2, 4, 6, 8, 10, 12, 14. 14 are on this structure. How many should I actually have? 10. So remember they're covalent. What can I force them to do? So share more, right? Do more bonded pairs versus lone pairs. So I'm going to say, look here, greedy nitrogen number 1. I'm taking your pair. And the other nitrogen, I'm taking your pair. And what am I doing now? Making a double bond to share. Okay, so I take away 2 and I add 1 back. So what's my count now? 2, 4, 6, 8, 10, 12. Dang it, what do I need to do? Do it again. Say, look here, greedy nitrogen. You can't have this one, and nor can you have this one. We're taking them and we're making you do what? Share again. Okay, what kind of bond is that? Triple bond. So correlate, give me some, or actually, the blue ones are nitrogen. Oh my god, how do you build this now? The blue ones are nitrogen. Build me a triple bond with nitrogen. There might only be enough for one of the nitrogens, so that way blue. Alright, she's Emily. So I think we're picking the incorrect bonds for some people. You're good. We gotta make it work. Alright, mix all of these up. Yours should look very similar to Nick's. Do you see the triple bonds need those flexi bonds? Flexi bonds. Alright. Alright, I want you guys to brainstorm for 30 seconds on the shape of this steel. The shape. You have 20 seconds left to tell me the shape. There's only one thing it could be. Oh, whoa. Did we say there was a central atom? There's no central atom. You gotta come up with this one by yourself. Tell me what it looks like. No, there's no central atom. You can't do that. Ignore the bonds. All right, Jacob, come here. Jacob, stay with me. All right, guys, ready? Look up here. Okay. What shape are we? A line. What's the shape for that? Linear. Don't get crazy on me. Those bonds are just there because we have to show a triple bond. How do you connect two dots? With a line. This is linear. This is where your common sense comes in. That's why the paper is only useful for something that have a central bond, but that one doesn't have a central bond. So if you just look at that and you look at it across, doesn't it just look like a straight line? Yeah? It's linear. I heard you guys going, it's trigonal pyramidal. No, not even close. It's not pyramidal. I know that the triple bonds do fully do that. All right, deassemble that one, and here's what we're going to do. I'm going to go ahead and have these 3 tables here, so Robbie's tables move, and then Jacob's going to pack your laptop, and then I'm going to have the rest of this go. I'm going to go ahead and introduce you to a PhET modeling system. Grab your laptop now, please. Grab your laptop now. Alright guys, can you get on, so the next group, go grab your laptops. This is those up your little modeling, you know. These 2 you guys are sharing, making it quite Alright guys, go to my website and I'm going to explain to you what's happening here. I typically need 2. Alright, so as your laptops are pulling up, some of this sometimes will take a little while. Does everybody have theirs kind of just logging on for me? Mostly? Okay. So what we're going to do is I'm going to continue helping you with your sheet in terms of your bond electronegativity differences, but I'll do one more sample for you. But what we're going to do is we're going to learn more about how these look in 3D, and the geometries that go along with them, the molecular geometry, which we were talking about, plus the electron group geometry, which is a slightly different way of looking at it. It's just basically you count everything as a ligand versus electrons, and then separately atoms. So that's what this PhET simulation will go through. As you do this, you're going to see bond angles, and that's what this sheet is for. So as you go through it, you're going to be working with a partner on this at your desk tables. And I've got a couple people who don't have a partner at their desk tables today. So what I can do is I can have some people move. But I want you to be at your desk your desk groups, because that gives you a chance to ask people across from you, like, hey, I don't understand this part. Can you help me out here? So that way you have another pair to work with. So you're going to be working in pairs. That's why I have one sheet. So you guys can trade off drawing and answering things. One person can pull up a simulation. One person can pull up a simulation. One person can be drawing, vice versa. So on the sheet, you'll see molecules and then MG. You see on the sheet where it says MG? MG is molecular geometry. So just like, you know, tetrahedral, trigonoplanar, trigonopyramidal, you'll see a couple of those. And then octet met, and you were going to say yes or no. On the back, there are some other drawings. So you guys are going to have about 45 minutes for this right now. Before you even get to this, though, I want you to watch it's like a 3 or 4 minute video on VSEPR theory. And it's a TED Ed. It's really good. It helps you understand the shapes a bit more. And those 2 links are under homework for tonight. Okay? So they're not homework for tonight. They're just linked under homework for tonight. So I want you to get as much done as you can in class. And you can start figuring it on the website. If you want to go ahead and establish a partner, establish a partner now. You want to work with Miles or one of them that don't work